In the quiet rolling hills of Milton, Pennsylvania, stands a colossus of food engineering that operates with the relentless rhythm of a mechanical heart. This facility, one of the largest canned food plants in the world, is the epicenter of a culinary logistical feat that transforms raw agricultural commodities into millions of shelf-stable meals every week. To witness the production of Chef Boyardee beef ravioli is not merely to watch a cooking process. It is to observe a triumph of fluid dynamics, thermodynamics, and high-speed automation working in perfect synchronization. The journey of a single can, from a collection of dry powders and raw proteins to a vacuum-sealed vessel capable of lasting years on a pantry shelf, reveals the intricate science of modern food preservation and the sheer magnitude of industrial scale. The genesis of the ravioli begins in the bulk receiving area, a cavernous space designed to handle ingredients not by the pound, but by the ton. The structural integrity of the pasta shell is paramount, and it relies entirely on the quality of the semolina flour. This flour, milled from hard durum wheat, is chosen specifically for its high protein content and robust gluten structure. It arrives in pneumatic tanker trucks, which blow the flour into towering silos that loom over the factory. From these silos, the flour is airlifted through a labyrinth of pipes directly into the mixing room. Here, the science of hydration takes center stage. Industrial mixers, capable of handling thousands of pounds of dough at once, combine the semolina with precise ratios of water. Unlike a home kitchen where dough is treated gently, these machines apply immense torque to force water into the protein matrix of the wheat. This high-energy mixing is critical. It aligns the gluten strands to create a dough with high tensile strength, a property necessary to withstand the mechanical violence of the canning line without disintegrating. While the gluten network is developing in the mixers, a separate but equally complex process occurs in the meat preparation zone. The beef filling is a carefully engineered composite designed to remain moist despite the high heat sterilization process that follows later. Blocks of beef are fed into heavy-duty grinders that extrude the meat through perforated plates, reducing the muscle tissue to a uniform particle size. However, ground beef alone shrinks and expels water when cooked. To counteract this, food scientists utilize a mixture of textured vegetable protein and cracker meal. These ingredients act as a sponge matrix. When mixed with the beef in massive stainless steel blenders, they absorb the rendered fats and juices that would otherwise separate during cooking. This mixture is seasoned with a proprietary blend of spices, garlic powder, onion powder, and salt, ensuring that the flavor profile remains consistent across millions of units. The result is a filling that is texturally homogeneous and chemically stable, ready for encapsulation. The convergence of dough and meat occurs at the forming station, a machine that operates with the precision of a printing press. The crumbly, hydrated dough is fed through a series of reduction rollers. These steel cylinders compress the dough with thousands of pounds of pressure, transforming it from a loose mass into continuous, silky ribbons. Laser sensors constantly monitor the thickness of these sheets. If the pasta is even a fraction of a millimeter too thick, the mouthfeel will be gummy. Too thin, and the ravioli will rupture. Two parallel sheets of pasta travel toward the die assembly. As the bottom sheet moves forward, a positive displacement pump injects precise spheres of the meat filling onto the surface at a rapid cadence. The top sheet is immediately laid over the filling, creating a pasta meat sandwich. A rotating die cutter then presses down, performing two functions simultaneously. It crimps the two sheets together to form a seal and cuts the ravioli into its signature square shape with serrated edges. The web, the excess dough between the squares, is stripped away and pneumatically returned to the start of the line to be reground and reused, ensuring near zero material waste. At this stage, the ravioli are technically raw and fragile. Before they can endure the canning process, they must undergo starch retrogradation. The ravioli travel through a blanching tunnel, a steam-injected chamber that par cooks the pasta. This brief exposure to intense heat gelatinizes the starches on the surface of the dough, firming up the structure and preventing the ravioli from sticking together in clumps. Emerging from the blancher, the pasta is resilient and ready for the filler. Meanwhile, the sauce, the liquid medium of the product, has been prepared in an adjacent hall of kettles. This sauce is a suspension of tomato paste, water, high fructose corn syrup, and spices. It is heated in steam-jacketed kettles to a specific viscosity. The temperature control here is vital. The sauce must be hot enough to flow rapidly, but viscous enough to suspend the ravioli evenly within the can. The canning line is where the operation reaches its highest velocity. Empty steel cans, having been depalletized and inverted for an air-jet cleaning to remove dust, race along magnetic conveyors at speeds that blur the vision. They approach the volumetric filler, a rotary machine that operates like a carousel. As the cans spin underneath, the machine drops a measured amount of the par-cooked ravioli into each vessel. Immediately downstream, a piston filler floods the can with the hot tomato sauce. This step is governed by the principles of fluid displacement. The sauce fills the voids between the pasta pillows, but crucially, the machine is calibrated to leave a specific volume of empty space at the top of the can, known as headspace. This headspace is a critical safety feature. It allows for the thermal expansion of the contents during the cooking phase. Without this air gap, the internal pressure generated by heating would distort the metal can or cause the seals to fail. Once filled, the cans move to the seamer, perhaps the most mechanically precise instrument on the floor. In a fraction of a second, a lid is placed on the can, and a chuck spins the can while rollers crimp the flange of the lid and the body of the can together. This forms a double seam, a hermetic seal that is airtight and impervious to bacteria. At this precise moment, the ravioli inside are sealed, but not sterile. The interior environment is anaerobic, and without further treatment, it would be a breeding ground for pathogens. To achieve shelf stability, the cans must undergo thermal processing in a massive apparatus known as a hydrostatic cooker. The hydrostatic cooker is a towering engineering marvel that functions as a continuous, high-pressure retort. It utilizes the weight of water columns to maintain pressure within a central steam chamber. The sealed cans are loaded onto a carrier chain that loops them up and down through these water towers. As the cans descend into the machine, the pressure increases, allowing the cans to enter a steam environment that exceeds the boiling point of water, typically around 250 degrees Fahrenheit, 121 degrees Celsius. This is the critical control point for food safety. The cans spend a predetermined amount of time in this high heat zone, a duration calculated to ensure commercial sterility. The heat energy must penetrate from the outside of the can through the sauce and into the geometric center of the meat filling. This thermal lethality step destroys all microorganisms, including spores of Clostridium botulinum, rendering the food safe to eat indefinitely as long as the seal remains intact. Following the sterilization phase, the cans must be cooled, but they cannot simply be ejected into room temperature air, as the pressure difference would cause them to buckle. Instead, they travel through a cooling leg of the hydrostatic cooker, where they are submerged in progressively cooler water. This controlled cooling process collapses the steam inside the headspace of the can, creating a vacuum. This internal vacuum is essential. It pulls the flexible metal lid slightly inward, creating the concave safety button that consumers recognize. This vacuum also restricts the movement of the product inside, preventing physical damage during transport. Emerging from the cooker dripping wet, the cans are subjected to high-velocity air knives, blades of compressed air that shear water droplets off the metal surface. A dry surface is necessary for the next step, labeling. The cans roll through a high-speed labeler that applies a precise strip of glue and wraps the iconic paper label around the cylinder. Even at this late stage, the science of quality control remains active. The cans pass through X-ray detectors and vision systems. These machines analyze the density of the contents to ensure no foreign materials are present and verify that the fill level meets regulatory standards. If a can is dented, the label is crooked, or the vacuum is insufficient, an automated rejection arm kicks it off the line instantly. The final phase of the process is purely logistical. Robotic palletizers arrange the finished cans into trays and stack them onto wooden pallets. The pallets are wrapped in tensioned plastic film to secure the load for the dynamic forces of trucking and rail transport. Forklifts whisk the pallets away to a warehouse the size of several football fields, where they are organized by lot codes for distribution. From the molecular alignment of wheat protein to the thermal destruction of bacteria, the production of Chef Boyardee beef ravioli is a testament to the sophistication of modern food science. It is a process that relies on the immutable laws of physics and chemistry to deliver a consistent, safe, and hot meal to millions of tables, bridging the gap between agricultural raw materials and the modern consumer with industrial precision.